When the James Webb Space Telescope opened its massive golden eye to the early universe, few of us expected a mystery of this scale. I'm Michio Kaku, and today we're going to explore something that has shaken the foundations of cosmology, something astronomers are calling the little red dots. These tiny, extremely compact, intensely red galaxies have appeared in Webb's deepest images like cosmic embers scattered across time. They are small, but they are far from simple. Their properties don't match our models, they don't behave like ordinary star-forming galaxies, and they refuse to fit neatly inside any known category. And so, scientists now believe they might be the missing evolutionary stage that connects dense starburst galaxies to the very first massive black holes. The story begins with Webb's early deep field surveys in late 2022, when astronomers pointed the telescope toward patches of sky that looked empty through previous instruments. But Webb, with its infrared sensitivity, sees what Hubble cannot, the earliest light in the universe. Suddenly, dozens of faint red compact sources appeared. They were located at redshifts between 4 and 8, meaning the light reaching us today left when the universe was only about 600 million to 1.5 billion years old. That's the cosmic toddler stage. And yet these objects didn't look like toddlers at all. They looked like miniature powerhouses, hundreds of light years across, extremely bright in the infrared, and so red that astronomers immediately suspected something unusual was happening in their cores. Many galaxies from that era were expected to be messy, clumpy, and relatively large. But these little red dots were tiny, so compact that if you placed one inside our Milky Way, it would sit comfortably inside our solar neighborhood. These early galaxies were packing enormous amounts of matter into microscopic volumes. Something intense was happening inside them, and that triggered the first major debate. Some astronomers argued that these must be ultra-compact starburst galaxies. In that case, the red light would come from dust heated by vigorous star formation. Imagine hundreds of millions of young stars being born in a cosmic pressure cooker. The accumulated dust would glow red under Webb's infrared filters. Others argued that the red color and brightness were signs of something far more exotic, massive black holes actively feeding in their centers. These early active galactic nuclei, or AGNs, would produce the broad spectral lines we see and explain the incredible velocities measured inside the little red dots. And yet, something didn't add up. When Webb later captured spectroscopic data from these objects, scientists noticed extremely broad Balmer emission lines. These lines suggested gas moving at thousands of kilometers per second, motions typically associated with either the gravitational pull of a black hole or extreme turbulence in a dense star-forming environment. But neither explanation fit perfectly. If these galaxies were powered by black holes, we would expect X-ray emissions, lots of them. Yet most little red dots showed almost no X-rays. Conversely, if they were purely starburst galaxies, the velocities were too high for normal stellar systems to sustain. A purely stellar core shouldn't be able to achieve such gravitational binding without collapsing under its own weight. This contradiction placed astronomers in a peculiar situation. Both interpretations explained some of the evidence, but neither explained all of it. These objects were too red, too fast, too compact, and too quiet in X-rays. They lived in a space between categories, a cosmic twilight zone. And in science, when an object refuses to behave, it's usually because it represents something new. As scientists wrestled with this puzzle, a new idea emerged, one that could rewrite our understanding of galaxy evolution. A recent study led by astronomer Andres Escala suggested that maybe we shouldn't treat the two models, stellar-only and black hole-dominated, as opposing hypotheses. Instead, what if they describe two stages of the same evolutionary process? Imagine a galaxy born as an ultra-dense star-forming system. Over time, its central regions grow so compact and so gravitationally intense that they begin to collapse. That collapse creates the seed, or rapidly expands an existing seed, of a massive black hole. Eventually, this black hole ignites, entering the active nucleus phase we associate with quasars and AGNs. According to this view, the little red dots are caught in the middle of this transformation, frozen in time for us to observe exactly when the black hole has begun to form, but before it has fully lit up. This would also explain the missing X-rays. A black hole in its earliest stages of growth might not yet have formed the hot, powerful accretion disk needed to produce strong, high-energy emissions. It would be a cosmic infant, growing quietly, still wrapped in the dense stellar cocoon that created it. The reason we don't see little red dots at lower redshifts is that this transitional phase is incredibly brief. They appear only in the early universe because that is the only era when such dense environments were common enough to form the first massive black holes. Let me give you a sense of the scientific importance here. One of the greatest mysteries in astrophysics is how supermassive black holes, millions to billions of times the mass of the Sun, appeared so early. Some quasars we observe today existed when the universe was less than 1 billion years old, yet their black holes were already enormous. How did they grow so quickly? Traditional models required exotic physics, direct collapse black holes, massive primordial seeds, or runaway mergers of giant stars. But if little red dots really are the direct ancestors of early supermassive black holes, then the answer may be simpler and more elegant than we thought. Perhaps black holes didn't need exotic formation mechanisms. Perhaps they grew rapidly simply because they were born inside incredibly dense star clusters, where the gravitational collapse of the core could trigger black hole growth on fast timescales. This means the earliest galaxies weren't just star factories, they were black hole factories. And the little red dots are the fossils of that process. Webb's observations also suggest a surprising relationship between these young galaxies and the black holes inside them. In the modern universe, a central black hole is usually about 0.1% of its galaxy's mass. But in the little red dots, the black hole might be 10% of the galaxy's mass, 100 times larger proportionally. This flips our understanding of galaxy evolution. Instead of galaxies shaping their black holes, early black holes may have shaped their galaxies. What we are seeing, perhaps for the first time, is the moment when the roles were reversed, when the black hole was not the outcome of the galaxy, but the engine that would determine its fate. And that is why the little red dots may be one of the most important discoveries of our generation. As astronomers collected more data from the James Webb Space Telescope, the mystery of the little red dots deepened. I'm Michio Kaku, and as we continue this journey through the early universe, we now shift from what these objects are to why they matter, and how they may rewrite our understanding of cosmic evolution. The little red dots are not simply anomalies in Webb's images. They are windows into a time when the laws of structure formation were playing out with extraordinary intensity. And what we're discovering is that this brief cosmic era may hold the secret to how galaxies and black holes co-evolved from the very beginning. When we look at these little red dots, we are witnessing a level of compactness that is nearly unprecedented. Imagine packing billions of stars into a region only a few hundred light years across. The gravitational pressure alone would be enough to crush the core into an extremely dense environment. In such conditions, the traditional balance between radiation pressure, gas dynamics, and stellar winds may no longer hold. Instead, gravity dominates ruthlessly. It is in places like these that nature becomes capable of forming massive black holes at extraordinary speeds. But to understand why this is so revolutionary, we need to step back and consider one of the greatest puzzles in astrophysics. How did black holes reach monstrous sizes in such a short amount of time? Some quasars we observe at redshift 7 already contain black holes 1 billion times the mass of the Sun. To grow that large so early, these black holes would have needed a head start. For years, scientists proposed exotic mechanisms, direct collapse of enormous primordial gas clouds, or massive population 3 stars collapsing into unusually heavy seeds. But each scenario came with complications. None fully explained the rapid growth we observe. The little red dots may change that by introducing a simpler, more natural pathway. In Escala's evolutionary model, galaxies first undergo a phase of extreme star formation, compressing matter into a dense, star-dominated core. As the density increases, the core becomes unstable, eventually collapsing and initiating the rapid growth of a central black hole. The black hole then accelerates its growth by feeding on the surrounding dense gas, eventually becoming powerful enough to ignite as an active nucleus. This means that black holes didn't need exotic physics. They just needed the extraordinary environments that existed in the early universe. This is a monumental shift in our understanding. Instead of black holes forming outside of galaxies or through rare special events, they may have been a natural byproduct of galaxy formation itself. The little red dots represent that moment of transition, the cosmic tipping point when a dense cluster of stars begins its metamorphosis into a galaxy dominated by a central black hole. But the evidence is not just in the spectral lines or the red color. When astronomers analyze the velocity dispersions inside these objects, the numbers are astonishing. Gas within these galaxies appears to be moving at unusually high speeds. In many cases, the internal velocities are far too high to be supported by normal stellar dynamics. Something heavy must be lurking in the core, something exerting far more gravitational influence than a typical star cluster. And yet, the lack of strong X-ray emission shows that whatever this central engine is, it has not yet entered the fully active AGN phase. This is exactly what we would expect if we were catching these objects right before ignition. A black hole that is still forming or just beginning to accrete matter may not produce the intense radiation signatures that make AGNs so bright. Instead, it might be shrouded by the dense stellar environment around it, hiding in plain sight. These early pre-AGN phases would be short-lived, making them incredibly rare. And that rarity is precisely what Webb is now revealing. Their scarcity at lower redshifts supports the idea that this is a transitional moment in galaxy evolution, visible only during the first billion years of cosmic history. Now, consider the implications of this. If the little red dots are indeed the seeds of supermassive black holes, then the early universe was far more efficient at creating them than we previously thought. Instead of slowly growing through accretion over billions of years, black holes could have reached enormous masses in a fraction of that time simply because they were born inside dense stellar environments. This would explain how early quasars emerged so quickly without resorting to speculative physics. The early universe was a crucible for rapid gravitational collapse, and Webb is giving us the first clear snapshots of that process. But there's another layer to this. In the local universe, black holes and their host galaxies have a well-established relationship. The mass of a galaxy's central black hole scales with the mass of its bulge. But when we look at the little red dots, we find something shocking. The central black hole may account for up to 10% of the total mass of the galaxy, 100 times the proportional mass seen in modern galaxies. This means the relationship between galaxies and their black holes has evolved over time. In the early universe, black holes may have formed first and then shaped the galaxies around them. Later in cosmic history, the balance shifted, with galaxies and black holes growing together. This new perspective forces us to rethink the coevolution narrative. Instead of galaxy growth regulating black hole growth, the earliest black holes may have played a dominant role in shaping their galaxies' structures, star formation rates, and overall evolution. The little red dots hint at a dynamic, feedback-driven universe where the seeds of massive black holes dictated the architecture of early galaxies. We may be looking at the very beginning of the galaxy-black hole connection, an evolutionary relationship that would define the structure of the cosmos for billions of years. To test this idea, astronomers now rely on multiple observational techniques. Deep X-ray campaigns will search for faint accretion signals that could confirm the pre-AGN phase. Infrared spectroscopy will refine our understanding of the velocity dispersions and stellar populations within these objects. Radio and submillimeter telescopes may detect the earliest outflows or jets associated with nascent black holes. And future surveys with the Nancy Grace Roman Space Telescope and the Square Kilometer Array will dramatically increase the number of known little red dots, allowing scientists to build a statistical picture of how common this evolutionary phase truly was. With each new data set, the mystery becomes clearer and the narrative becomes more compelling. We may have discovered the missing evolutionary link between dense star-forming galaxies and the first massive black holes. And if that is true, then the little red dots are not merely a curiosity. They are the key to unlocking one of the most profound chapters in cosmic history. As we arrive at the final part of this journey, I want you to imagine something extraordinary. Somewhere in the vast darkness of the early universe, inside regions smaller than our cosmic neighborhood, a transformation was unfolding. A transformation so powerful that it would shape the structure of galaxies for billions of years to come. I'm Michio Kaku, and what we've been exploring through the mystery of the little red dots is nothing less than the origin story of supermassive black holes, the cosmic engines that sculpt galaxies, regulate star formation, and anchor the architecture of the universe itself. And now, as we look toward the future, we must ask, what comes next? What will the next generation of telescopes and data reveal about these tiny crimson beacons at the edge of time? The little red dots are more than just peculiar cosmic objects. They represent a missing chapter of a story that astronomers have been struggling to complete. If Escala's evolutionary model is correct, then Webb has captured these galaxies at a precise moment, one so brief, so delicate, that it almost feels miraculous we are able to witness it at all. This is the moment before ignition, when the black hole at the center of a dense galactic core is forming, but not yet unleashing the full fury of an active galactic nucleus. It is the moment when gravity tightens its grip, when gas swirls inward, when the seeds of a cosmic titan are planted. And this offers a breathtaking insight into how black holes could reach supermassive status so early in the universe's timeline. Instead of long, drawn-out accretion histories, the initial growth may have been extraordinarily fast, driven by the extreme densities of early star-forming environments. In such regions, matter piles up like sand, collapsing into a sinkhole. Gravity becomes a runaway force. The central core is crushed, the black hole grows rapidly, and before long, the quiet pre-AGN object becomes a brilliant beacon, one of the quasars we observe shining across the universe. But what truly excites astronomers is not just the discovery of these objects. It is what they imply about cosmic evolution. The relationship between galaxies and their central black holes may have begun in a completely different way than we assumed. Instead of black holes quietly forming at the center of large galaxies, the earliest black holes may have led the way. They may have dictated the shape, mass, and behavior of their galaxies from the very beginning. In essence, black holes may not have been passengers, they were the drivers. This perspective reshapes our understanding of the universe. It suggests that the growth of structure was not a slow, orderly process, but a violent, dynamic, feedback-driven dance between gravity, gas, stars, and the dark hearts forming at the center of these early systems. And by studying the little red dots, we are getting closer to watching that dance unfold in real time. The next step is to test this model. Deep X-ray campaigns will search for the faintest whispers of accretion. Powerful radio arrays will attempt to detect signs of early jets or outflows. Infrared spectroscopy will refine our measurements of mass, dispersion, and star formation. But perhaps the most exciting prospect is the arrival of the Nancy Grace Roman Space Telescope and the Square Kilometer Array. These instruments will allow astronomers to survey vast areas of the sky with unprecedented detail, potentially uncovering thousands of new little red dots. For the first time, we will be able to build a statistical picture of how common this evolutionary phase truly was, and whether it represents the primary pathway to supermassive black hole formation. If the little red dot phase turns out to be brief, as the model predicts, That would explain why we only see these objects at high redshifts. They appear only in the earliest eras, because that is when the physical conditions of the universe favored the formation of such dense structures. Later on, the expanding universe and falling gas densities would make this pathway rare or even impossible. And that means Webb may be giving us a once-in-a-lifetime window into a cosmic process that no longer occurs today. As we close this story, I want you to consider the significance of that. For decades, scientists have searched for the origin of supermassive black holes, those cosmic monsters lurking in the hearts of galaxies. But the universe does not often reveal its secrets willingly. It hides them behind walls of distance, dust, and time. Yet here we are, with Webb's infrared eyes cutting through that darkness, giving us a glimpse of the birthplaces of these celestial giants. The little red dots are tiny, but they carry enormous implications. They remind us that the universe is still full of surprises, and that every new discovery opens the door to even deeper mysteries. They teach us that science is not a collection of answers, but a journey driven by curiosity, powered by imagination, and guided by the tools we build to explore the cosmos. Perhaps the most beautiful truth is this: we are living in an era where humanity can finally watch the universe reveal its earliest chapters. And somewhere in that ancient light captured by Webb, the seeds of black holes, seeds that would one day anchor galaxies like our own, are shining faintly, waiting for us to understand them. And that, in many ways, is the magic of science. The more we learn, the more wondrous the universe becomes.